So we are applying the derivative. I've given you the problem when the flea jumps, and we've analyzed almost all parts of his jump at this point, with the exception of part F. This asks, when does the flea land, or when does it return to its initial height, and at what is the rate at that time, and is it increasing or decreasing? So let's take this one question at a time. When does the flea land, or when does the flea return to its initial height? So to help us answer this question, we're going to reference the graph. Now, we drew this by hand, but I have lots of different markings of it here, so I just recopied this from my calculator. All right, if we want to figure out when the flea starts his jump, that is, of course, going to be right here at 0. Remember, our x-axis is an application of t, or time, and we know that time has to be positive, so this is where the very first part of the jump starts. Now, if we want to figure out when the flea lands, we want to figure out when does it come back to that same height, and that is right here. So basically, we are trying to find the x-intercepts of this graph. Well, that's awesome because we've actually already computed that. We did compute that in the first video, or in the first section. We found our x-intercepts. So the first one was t equals 0 when the flea starts his jump, and the last one is when t equals 0.898, or when the flea lands his jump. Now, our graph goes beyond that. At this point, it goes down here. But remember, our y-axis stands for h of t, which stands in meters. So I can only have a positive distance, or I can only have a positive meters. So basically, all of this graph down here doesn't apply, just like all of this graph here doesn't apply. So the only part of this graph that fits in is within the first coordinate. Okay, so we just said, when does the flea land? That is at our x-intercept, and we solved that by setting our equation equal to 0. Now, I'm not going to do the math again, but we figured out t equals 0. That's when he starts his jump, and when t equaled 0.898. So that's when the flea lands. We need a label. T is in seconds, so approximately 0.898 seconds. The second question then asks, at what rate is our h of t, or our function, changing at this time? Well, the rate is given by the derivative equation, which we computed in part D, gave us 4.4 minus 9.8t. So if we want the rate at that specific time, all we have to do then is plug that specific time into our equation. So h prime of 0.898 just doing the math in one big step is approximately negative 4.4 here. Now we need to label this. We said we are computing rate. Rate is something per something, and just like any other part of the problem, this was meters per second. So at the very end part of the jump, the flea is going negative 4.4 meters per second. The last question, is it increasing or decreasing? Well, since our rate was negative at that time, we know that he is decreasing at that time. And that matches with what our graph is. We said from the peak of the graph to the right of the graph, our flea's rate is decreasing because he's on the descend of his jump. So that is the last part there. Okay, so we have finished all parts A through F of this question here. Now, your homework might not have all parts of this, or it might not all be worded the exact same way, but I have taken every different example that I possibly can think of and contained it into this problem. So you should be able to take all of this application here and be able to apply it to any kind of problem that is similar to this. You just have to figure out which part that it matches the most closely to, and then adapt it to that specific applied problem on your homework. So I've given you all the information that you need to solve any kind of problem that is similar to this on your homework.